Welcome to video number 19 in the game theory sequence. This video is about the notion of weak sequential equilibrium. So in games with perfect information, we saw that the notion of Nash equilibrium does not always give a good answer to the question, what is a rational solution of particular game, because there are some Nash equilibria that have to be discarded as not being sensible solutions. For example, because they involve incredible threats. In general, games with possibly well, and I should add that so the way to solve a perfect information game is to use the notion of backward induction. A backward induction solution is still a strategy profile, and it is always a Nash equilibrium, but by using backward induction you eliminate potentially other Nash equilibria which cannot be taken to be reasonable solutions of the game. When we move to general extensive form games, which might have imperfect information, then we have the same problem, that some Nash equilibria might not be sensible solutions of the game. And so what we do is we generalize the notion of backward induction, and the generalization is called subgame perfect equilibrium, which coincides with backward induction if the game has perfect information, and otherwise it's a more general procedure that can be applied to games with possibly imperfect information. And again, we might find a game that has say one subgame perfect equilibrium but more than one Nash equilibrium. Then that means that the Nash equilibria that are not picked by the notion of subgame perfection are to be considered not good solutions of the game, not reasonable solutions of the game. So the question I want to ask now is, does the notion of subgame perfect equilibrium always do a good job? And here we have a game where player 1 either terminates the game by playing R or gives the move to player 2 by playing either L or M, but player 2 is not informed about what player 1 chose, if player 1 chose L or M, and is only told that player 1 chose L or M, and has to make her choice between W and E in this situation of imperfect information, and the payoffs are as they're written there. So we could try to solve this game using the notion of subgame perfect equilibrium, but the thing to notice about this game is that this game has no proper subgames. Now, the way in which the notion of subgame perfect equilibrium refines the notion of Nash equilibrium is by requiring that the solution, which is a strategy profile, be not only a Nash equilibrium for the entire game, but also a Nash equilibrium in every proper subgame. Of course, if there are no proper subgames, then the restriction becomes vacuous. And in this kind of games, where there are no proper subgames, the set of Nash equilibria coincides with the set of subgame perfect equilibria. So finding a subgame perfect equilibrium for this game is the same thing as finding a Nash equilibrium. So to find the Nash equilibria, we can draw the strategic form associated with this game. This is a very simple game. Each player has only one information set. Player 1's information set is just a single node, and there he has three choices. So player 1 has three strategies, LMR, and player 2 has only one information set, two choices there, W and E, so we have a 3x2 matrix. And if you fill in the cells, then you get the strategic form that is written on the right. And to find a Nash equilibrium, highlight, I'll circle in each column the largest payoff of player 1, and in each row the largest payoff of player 2. That would be 1 in the first row, 2 in the second row. There are 2 instances of 3 in the third row. And then any cell where both payoffs have been circled or highlighted is a Nash equilibrium. So there are 2 Nash equilibria. In this game, one is LW and the other one is RE, and they're both subgame perfect equilibria precisely because the restriction that is used to define a subgame perfect equilibrium, namely that in every subgame, proper subgame, you should still have Nash, does not apply in this game. So does that mean that we should consider both Nash equilibria reasonable solutions of this game? Now I want to argue that one of these 2 Nash equilibria, RE, is a bad Nash equilibrium and should be rejected. On what grounds? Well, look at the player 2's strategy E, and place yourself at 2's information set. Imagine being player 2 having to decide what to do there. You've been told that it's your turn to move, you have to choose W or E. And as player 2 you would say, well, I don't know what player 1 did. Either he played L or he played M. Now, if I knew that player 1 had played L, what would I want to do? Well, in that case, if player 1 played L and I played W, I get 1. Whereas if I play E, I get 0. So if I knew that player 1 played L, then I would want to play W. What about if I knew that player 1 played M? Then in that case, if I play W, I get 2. If I play E, I get less, I get 1. So if I knew that player 1 played L, I would want to play W. And if I knew that player 1 played M, then I still would want to play W. Then I don't care that I don't have this information, that I don't know what player 1 did, because the choice of W is better in every situation that I consider in my mind. So W is the best choice. Okay? Now, what we have is that W strictly dominates E as a choice at 2's information set, but not as a strategy before the game begins. Right. As a strategy, if you look, if you compare W to E, so look at the strategic form, you have that against L, W gives 1, E gives 0, so W gives a higher payoffs. Against M, W gives 2, E gives 1, so W gives a larger payoff. But against R, W gives 3 and so does E, so you get the same payoff. What we have is that as a strategy, as a strategy, W weakly dominates E, not strictly, right? So in particular, if you're player 2 and you told me, I've decided to play E, I could not say, well, you must be irrational then. Because you could reply, no, I'm not irrational. I've come to the conclusion that player 1 will play R, and therefore my plan is just a hypothetical plan to play E, and is just as good as the alternative hypothetical plan to play W. My payoff is going to be 3, no matter what plan I make. Right? So it's not necessarily irrational as a strategy. So think of a strategy as a plan you make before you play the game. Then you can find a situation where that strategy is rational, and that would be the situation where player 1 plays R. On the other hand, the decision to play E becomes irrational once you actually have to make a choice between W and E. So when you actually are at your information set and you're told you have to move, knowing that you have to move, that player 1 did not choose R but chose either L or M, and you don't know which of the two, then you would have no way of justifying the choice of E, because whatever beliefs you have about what player 1 did, whether player 1 played L or M, you would always be strictly better off playing W rather than E. So this distinction between a choice, the notion of choice and the notion of strategy, is not picked by the notion of subgame perfect equilibrium. So a choice is you're actually there having to make a choice, whereas a strategy you can think of as a plan that you make before the play of the game begins. Okay? Now, because this game has no proper subgames, Nash equilibrium coincides with subgame perfect equilibrium. So RE is a bad Nash equilibrium, but it also necessarily a bad subgame perfect equilibrium, because they are just the same. So what we want to do is find a notion of equilibrium, a solution of a game, which can eliminate, say, RE as a solution to this game. Now, just using the notion of strategy profile will not do. And so we need to enlarge the object we are talking about from not just a strategy profile, but also something else. So this more complex notion is called an assessment. An assessment is a pair, sigma W, where sigma is a profile of behavioral strategies. From now on, we'll always assume that the payoffs are for Neumann-Morgenstern payoffs, so it makes sense to compute expected payoffs. And we know that we don't need to talk in terms of mixed strategies. We can use the simpler notion of behavioral strategy. And now we're adding something else, which is denoted here by mu and is called a system of beliefs. And the definition of a system of beliefs is a collection of probability distributions, one for every information set, over the nodes in that information set. So think again about the definition of behavioral strategy. That's also a collection of probability distributions, one for every information set. But these are probabilities over the actions there, over the choices there, whereas a system of beliefs is a collection of probability distributions, one for every information set, but the probabilities are on the nodes of the information set. So it's called a system of beliefs because it captures the idea of what beliefs a player could have at a particular information set. So, for example, for in this game, for player 2, we could say, imagine that player 2 is told that she has to move, that player 1 played L or M, and she could form some beliefs about what player 1 did. So she could say, well, I think it's equally likely that player 1 played L, so I attach probability half to the left node, which is the node that comes after the choice of L by player 1, and probability half to the right node, which comes after choice M of player 1. So this could be a belief of player 2, or player 2 could form a different belief and maybe become convinced that player 1 played M. So if she would attach probability, so let's do it in a different color, so there will be no confusion. So she could attach probability 0 to the left node and 1 to the right node. Another belief could be probability 2/3 to the left node and 1/3 to the right node, and so on. So mu takes care of specifying possible beliefs of all the players at all the information sets, the proper information sets, those that contain at least 2 nodes. For information sets that contain only 1 node, then the probability has to be 1 on that. You know that you are there. So here is a game with imperfect information. And notice that it's a game where there are no proper subgames. So any Nash equilibrium of this game is also subgame perfect, because the restriction that it should remain Nash in proper subgames does not have a bite, because there are no proper subgames. Okay, so let's pick an arbitrary system of beliefs. So sigma is the behavior strategy profile, which tells me that player 1 plays A with probability 1/6, B with probability 4/6, and C with probability 1/6. For player 2, we have that player 2 plays D with probability 1/3, E with probability 2/3. For player 2 at the right node, he plays F for sure, and for player 3 at the bottom information set, he plays H for sure, probability 1. And then we have these beliefs. So I named the nodes inside the information set. So let me enlarge this, and let's write these probabilities. So the beliefs that player 2 has at her information set on the left is probability 1/3 on the left node S, and probability 2/3 on the right node T. And the beliefs that player 3 has are probability 1/4 node U, probability 2/4 the middle node V, and probability 1/4 the right node X. So these are the beliefs, right? So these are the beliefs. And now we want to impose 2 conditions on an assessment to call it a good solution of the game, or a solution of the game. The first condition is called sequential rationality. Sequential rationality requires that at each information set, the action or the actions taken by the player who has to move there must be optimal given the player's beliefs at that information set, and given the subsequent strategies of his and of the other players. So let's check sequential rationality for this behavior strategy profile, sigma. Okay, so sequential rationality is a property of sigma, and let us check it. So let's start with player 3. Okay, so we are here, and we say if player 3 has these beliefs, then what should he do, right? Now, if he plays H, then with probability 1/4, it does so at node U, the left node, in which case his payoff is 0. And with probability 2/4, he is playing at node V, where with H he gets 4. And with probability 1/4, he is playing at node X, where his payoff is 0. So here we have that his expected payoff from playing H is 0. If he plays I, then with probability 1/4, he's doing so at node U, where he gets a payoff of 2. With probability 2/4, he's playing I at node V, where he gets a payoff of 1. And then with probability 1/4, he's playing at node X, where he gets a payoff of 2 by playing I. So we have 2 plus 2, 4, 6/4, which is 1.5. And so given these beliefs, H is the best choice, right? So given the beliefs that we have specified, H is the optimal choice. So now we go and check what choice is specified by sigma, and we see that in fact sigma says that player 1 chooses H with probability 1 for sure. So I'll write SQ for SR for sequentially rational. SR is equal to sequentially rational. Okay, so now let's look at player 2. Here, player 2, at the node on the right, we have that if player 2 plays G, then okay, so we are talking about this node here. If player 2 plays G, then for sure he's going to get 1, a payoff of 1. And if he plays F, then player 3, so we have the strategy of player 3 that we have specified is H with probability 1. So player 3 plays H with probability 1. So if you play F, it will be followed by H, and you get 2 if you are player 2. So F is optimal. This is the optimal choice, and that's exactly what the strategy profile sigma says that player 2 is doing. So F is also sequentially rational. Now let's look at this information set of player 2, the one on the left. Now if he plays D there, then with probability 1/3, he's doing that at node S, where D gives a payoff of 0. And with probability 2/3, he's doing it at node T, where D, followed by the fact that player 3 plays H, gives a payoff of 6. So that's 4. And if he plays E, then with probability 1/3, he's playing E at the left node, where he gets a payoff of 6. And with probability 2/3, he's playing E, then followed by H. That's what the strategy of player 3 says, and he gets a payoff of 3. So this is equal to 2 plus 2 equal to 4. So D and E are equally good, so they're both optimal. He gets a payoff of 4 if he plays D, he gets a payoff of 4 if he plays E, and so any mixture between D and E is also optimal. So also any mixture of D and E is optimal. So we have that this strategy profile is also sequential. So this not profile, the strategy, behavioral strategy of player 2 or part of player 2's behavioral strategy is also sequentially rational. And now let's do the calculations for player 1. So let's change to red. And we look at player 1 at the root. If player 1 plays A, then what happens? Then we have seen that player 2 plays D with probability 1/3 and E with probability 2/3, right? So if you play 1, you play A, then with probability 1/3, player 2 will continue with D and give you a payoff of 6, and with probability 2/3, player 2 will continue with E and give you a payoff of 0, so that's 2. If you play B, then with probability 1/3, player 2 will continue with D, and then we know that player 3 continues with H, so you will get 0. And with probability 2/3, player 2 plays E, then player 3 continues with H, and you get a payoff of 3. So this is equal to 6/3, which is 2. And finally, if you play C, then what? Well, then the strategy of player 2 is to, the behavioral strategy says that player 2 plays F here. So if you play C, then player 2 will follow with F, and player 3 will follow with H, and you end up with a payoff of 2. So they're all optimal, and so is any mixture of A, B, and C. So in particular, the mixture where you play A with probability 1/6, B with probability 4/6, and C with probability 1/6. So also that is sequentially rational. So the conclusion is that sigma is sequentially rational. So sequential rationality is a restriction we want the strategy profile to satisfy. And it's a restriction that makes use of the beliefs to check a property of the choices made in the strategy profile. So sequential rationality is the choices actually made with positive probability are optimal given the beliefs at the information set where the choices are made. Now, there is a second restriction that we want to impose, and this time it's on the beliefs. And now, to introduce this restriction, first of all, let us define the notion of a reachable assessment. Of a reachable information set given a strategy profile. Okay. So suppose I take the strategy profile sigma, where player 1 plays A with probability 1/2, B with probability 1/2, and C with probability 0. Player 2 plays, say, D with probability 1, E with probability 0 at the left information set, and plays F with probability 0, G with probability 1. And finally, player 3 chooses H with probability 1 and I with probability 0. So take this behavioral strategy profile, and then see which information set we get to with positive probability with this strategy profile. So we can highlight the choices that have positive probability, the A and B, and then D and E, and then G and H. And then see where you get from the root of the tree following highlighted choices. Any information set you can get to is called reachable, right? So the information set of player 2 on the left is reachable. This is reachable. Let me write it here. By sigma. So with probability 1, in fact, it is reached because player 1 plays either A or B with probability a half each. So with probability 1 you get there. This is not reachable because by sigma, because in order to reach that node of player 2, you need player 1 to play C with positive probability, but in this strategy profile, player 1 is playing C with 0 probability. And on the other hand, player 3's information set is reachable by sigma. Okay. So let me make a copy of this. And let's try a different strategy profile. The notion of reachability depends on the strategy profile you're considering. Okay, let's try now this following strategy profile. Now it's a pure strategy, so I can write it as A, D, F, and I, for example, right? If you want to be pedantic and write it as a behavior strategy profile, then you would write it as A probability 1, B probability 0, C probability 0, D probability 1, E probability 0, F probability 1, G probability 0, and then H probability 1, I probability 0. Okay, so whenever each player plays makes a choice with probability 1, then we can just write it more simply like that. So now if you highlight the strategies that are, so the choices that are played with positive probability, we have A, D, F, and I. So which information sets are reachable? This is reachable. In fact, it's reached with probability 1 because player 1 plays A. This node here is not reachable. And this node is not reachable. So this information set is not reachable. So not the node, but the information set is not reachable. Because to get there, you need either players 1 and 2 to play CF, but player 1 is not playing C, or players 1 and 2 to play BD or BE, but player 1 is not playing B. So even though player 2 is planning to play D, since player 1 is not playing B with positive probability, you cannot get to that information set. So the notion of reachable information set is of course, dependent on a behavioral strategy profile, and it's easy to determine. Okay, so then the second requirement that we impose is called consistency with Bayes' rule. And this requirement says that for information sets that are reachable, beliefs should be obtained using Bayes' rule. Okay, so it may be that you know what Bayes' rule is, but I will assume that you don't, or at least some of you don't. So I will now suspend this video and start a new one on Bayes' rule. And then once we have clarified what Bayes' rule is, we come back to this video and continue this analysis of how to solve extensive form games.